Welcome to the Go Gardening Show. This is going to be a wonderful episode. We're here at the Edwards Aquifer Authority Field Research Park, and I have two wonderful guests here.
Hi, I'm Jewell Cozort, a senior aquifer environmental scientist with the EAA.
And
I'm Pierce Lynch, a PhD student at UTSA.
well, we're going to do some wonderful soil work today, and first thing we're going to do is a soil probe right here.
Let's do it.
All right, Jewell, you're going to make me do something. I'm going to pull this line, and we're going to determine what a transect is. So you can tell me what a transect is while I'm doing all this wonderful work.
Sure. So here I have a transect tape, and we use it to establish 3 lines in our plot that we want to sample. It allows us to determine random sample locations, and we want to get a representative sample of the entire plot. So that's what our transect helps us do.
Well, now that we have the transect out, we're going to dig the hole, or the soil probe. So we didn't really discuss why we're actually doing these probes.
Thank you. Yes, that's an important aspect. So we have a study going on right now that it's looking at soil health. This is our baseline plot, but we're also comparing this to our Berman swale land management practice. Pierce and I have a study going on concurrently where I'm looking at dynamic soil properties of the soil health, like the physical, biological, and chemical properties, and Pierce is looking at the microbial communities.
That's really important. We discuss a lot of times the mineral content, but we don't often discuss the microfloral and the microfauna.
No, and the biology is really driven by the physical and the chemical properties of the soil.
So when we do the soil probes, you're taking this as your baseline and then comparing it to some of the treatment activities, which we're going to look at in a little bit.
That's right.
So that's wonderful. So shall we do it right now?
Yeah.
Let's do it.
Okay, let's go ahead and do it.
So what we would have is like a random sample list. We take 15 minimum soil samples and we composite them into one larger sample.
Okay.
That's what I then send off to the lab. So let's say one of the samples on my, one of the locations was 18 feet. I would come here, Pierce has our soil probe. We would clear the area of any
kind of organic matter that may contaminate the soil.
That's right.
Sample.
And then that looks good.
And we're only collecting the first 10 centimeters of soil. And so then we just put it in and pull it out. And this is one of our soil cores.
So that looks pretty uniform.
That looks like really great, dark, organic matter rich soil.
So I'm just going to relate this to the homeowner. Many of our viewers are homeowners. What would they expect? Is this something that they would expect to look at?
Well, I would think that homeowners in our region, we're in pretty clay soil, so I would expect a dark soil like this, but because we manage our lawns for non-native Bermuda grasses, most of us do. Some people may be overachievers and do native lawns. I would expect maybe a dark sample like this, but also it would probably be more compact and not as loose and as this.
And so as part of what you're doing is we're looking at this, and a homeowner, we probably would not see a really healthy, loose, full of microflora and microfauna in these samples here. A residential person would not see that.
No, not to the extent that an unmanaged plot would be, but it's hard to say because plant inputs do determine a lot of the biology in the soil.
All right.
And microorganisms are everywhere.
Yeah.
They are?
Even in poor soil.
They just might be a little bit different than the ones we find here.
Well, we're going to get another sample here, and this is in a treatment area. This is called the what?
Swale.
The swale treatment area. Okay, so we expect to have some differences between the baseline and the treated area. So let's probe away.
It does look different just off the bat. I can see some color differences here. Now the construction of the soil, if you can see the broader area, we had to dig out the topsoil layer to make the swale, to form it. And so we are left with the subsoil, or what was underneath. And for that reason, I would expect to see differences in texture.
And what would we expect to see?
So we're going to see differences in organic matter, texture, and the microbial community.
And the microbial community, yeah.
As a general rule, the lighter the soil, the less organic matter, as a general rule.
Yes.
Yeah, okay. So that's what we expect to find. And so you would take these two samples rather, to the lab and check them all out.
That's right.
And see, and so we're going to look at mineral content and the microflora and microfauna.
Yes.
Excellent. Okay. Well, here we are. We're in the swale. This is a depression in the soil, and you told us how they made it originally. What are we exactly looking for? We have a sensor here, and you have one in your hand.
That's right.
What exactly are we looking for?
So we talked about the soil samples, but we're also continuously monitoring water content, water temperature, electrical conductivity, and also water potential in these areas. And this is an example of our water content sensor. It's dug into the ground.
That looks dangerous.
Yeah, and it's very sharp, so be careful. But this is installed into the soil, and it continuously measures water content every 15 minutes. So what we've done here is we've built this swale along a contour of this hillside. And we expect rainflow or rainwater to flow over the surface and collect in the swale. And what we expect to see over time is increased soil moisture. And that's what we want to see, because we want to create conditions where water can seep into the ground and enter the water table, hopefully, or it will continue on in a downward path towards Cibolo Creek and contribute to the base flow there.
And so I can go this direction. That is Cibolo Creek,
That's
and underneath Cibolo Creek is?
The Edwards Aquifer.
That's right. So we are near the recharge zone, and so we're looking at different aspects of how maybe to improve infiltration and percolation.
That's right.
All right. What else are we looking for?
So we're also looking at the microbiology in the top 10 centimeters of soil, because water content drives microbial activity in soil. So here we'll collect the samples and then take them back to the lab, extract DNA, do a lot of bench work, and then analyze the communities for bacterial, archaeal, and fungal communities. And what we're seeing...
Ooh, what was that word again?
Bacterial and archaeal.
Archaeal?
Archaea?
Oh, archaea, okay. That's not Ikea, it's archaea.
archaeal.
Okay. Okay.
And fungal communities. And what we're seeing is that the swale is fostering a unique community that is significantly different than the other berm positions that we have created.
So the other side is different than what's on the bottom. Okay, now is that different from the samples that we took earlier in the baseline?
Yes.
All right, so actually what you're thinking is the water that's collecting in this, as well as maybe some debris, is really changing the microbial activity.
It's selecting for a really unique community within the soils in the swale.
Oh, so it's going to be different than either side. Okay, and you think that's because of the water collecting in here?
Yes, and I think it's partially the excavation of the topsoil and then compounded with the persistent saturation from stormwater runoff.
So they excavated the topsoil, and this is the subsoil, which is usually deficient in minerals and some microbial activity.
Yeah, there tends to be less microbial activity as you go deeper into the soil profile.
So what could increase soil moisture and microbial activity and nutrient levels?
Organic matter.
I knew it. I was leading you on that way. I was leading you to that point. So that's what we're saying. So organic matter. And so we like to relate this back to the homeowner. A lot of the research that we do here at the research park, Field Research Park. So if you're a homeowner, and we know construction practices probably remove the top layer of the soil, and all you're left is some of the substrates, the what we say, bee horizon on it. So what could you do to increase the nutrients and microbial activity, which we love in soil?
Yes, so I think introducing as much dead plant material on the top to have it decompose and it be incorporated into this top layer of soil as organic matter would really help, increase moisture retention, which is really important in our climate here in Texas. So if you have a lawn and you don't have an HOA that gets mad if you keep your grass clippings on top of your lawn, leave all of your removed plant matter on your yard to let it decompose naturally.
There's some new laws in Austin I can talk about, but
no.
that's for another show. So what else should we increase?
Well, the organic matter will not only increase and be beneficial to the microbial community, but the insect community as well. It'll enhance the water holding capacity of the soil. It just all in all is a really great practice to leave that organic matter. So lawn clippings, leaves, even adding compost. Some people will bring compost in and spread it throughout their yard, and that has been shown to increase the soil moisture.
Excellent.
If we're increasing the organic matter, if we're leaving those compost materials like lawn clippings and leaves in place, that's going to help over time reduce the amount of water we have to apply to our lawns, which is really important in our area to reduce our water use and promote native vegetation. All of that's going to help reduce the water coming from the Edwards Aquifer.
And that's a key aspect of the Edwards Aquifer Authority is helping with conservation for everyone. All 2.2 million users of the aquifer.
Yes.
One last very important thing is we're here at the Field Research Park, and it involves the EAA and what?
So we're here, and all of this research is possible because we're on a conservation easement. And I just wanted to highlight that this land will be held in perpetuity as a conservation easement that will directly benefit the Edwards Aquifer, our water quality, and our water quantity.
And you can do the research here.
We can do the research here, and another really important aspect is our partnership with universities like UTSA and Pierce here. So we want to thank you very much for being with us.
So conservation easements can involve a lot of people, City of San Antonio, what other ones, just a lot of other different entities. Nature Conservancy can have nature conservation easements, so that's just really wonderful. So I'm so glad you're here, holding the water, holding the land in perpetuity, doing wonderful research, and I want to thank both of you. I want to thank Pierce for her wonderful explanation of soil microbial action, and I want to thank Jewell for explaining how to do a transect and how to dig. So thank you so much, very much, for allowing us a video here today.
And thank you, Mark.
And thank you for watching the Go Gardening Show. Let's get out there and garden and
save some water.